George Eaglebow lecture on fit statistics, and Fred can peek if he wants to. Here we go. First of all, X for the observation. We're going to just do dichotomies because that's complicated enough for us guys. If we can handle the dichotomy problem, we'll be able to do a great deal. Now, the reason you have a model is so you know what to expect the response to be. A response by itself is worthless unless you have a model for it. And I'm going to say something that Fred told me at lunch today, and that is that the way Michelangelo worked, he found a piece of marble in which he could see something worth carving, and then he liberated the form from the marble. Well, it's the same thing. This is like the marble, and it's not worth anything unless we see something in it. If we see something in it, then we know what to expect, and we expect something of X. And in this case, we expect X to be the value of P, where P is the person and an item, where P is modeled by our favorite mechanism for defining measurement, namely the good old Rasch model. And we also know what the variance of X is supposed to be. It's P1 minus P, which I'm going to call Q in order to save chalk. Now, I'm not going to carry the subscripts around anymore because I think we just know that they're always there. Now, once we've got that, this is what we observe, this is what it means to us. We can now make a comparison between what we observe and what we think and get a residual, that is X minus P, that's the score residual. Or we can standardize that and get a Z, which is X minus P, that's Y, divided by the square root of Q, and that's the usual standard residual. This one we expect will equal 0, but its variance is Q, the same as X, because that's a constant. This one has been standardized by dividing by the standard, the square root of its variance. So this one we expect to be 0 with a variance of 1. And for more on this, look at rating scale analysis, page 100, where it's all diagrammed out. Now, what about fit? Well, let's look at the data. We have observed the data matrix, X. We have produced a residual matrix, Y, or a standard residual matrix, Z. These matrices all have the same structure. They're n people taking L items. This is the data. And this is the residuals from expectation, either in score form or in standard form. Now, all fit analysis is based on this or this. There isn't any other information about fit available. This is the complete information because this is the discrepancy between what we think and what we see, what we mean and what we've got to work with. So, let's look at one of these matrices. Take the Y matrix. We can identify any set of Y's. Like for one person, that would be his string of Y's right here. Or we can identify them with a string of Z. Or for an item, take a string of Z's or Y. Or for a combination of some people and some items, a little block or submatrix inside of this matrix. Any subset in here, this is the Y matrix, any subset in here can be used as a fit analysis. If we look at this subset, we're looking at the fit or misfit of that person over all of the items he took. If we look at this subset down here, we're looking at the fit or misfit of a particular item. If we look at this here, we're looking at the way a certain group of items is dealt with by a certain group of people. So here we're looking at bias. Are these items favoring these people or not? These might be the girls. These might be the sewing items. These might be the boys. These might be the bicycle repair items. These might be the French-speaking children. These might be the items with words derived from French in them. So this is the bias. Now, in order to do the fit of a person, we will add up either the square of the y's or the square of the z's. We'll divide it by its expected value. In this case it's q, in this case it's 1. And that will give us a statistic, u or v, which is a mean square statistic. This one has been called infit for reasons I'll explain in a moment. And this is called outfit for reasons. And these are two ways to summarize a string of a person's string of residuals or an item's string of residuals. In this case, well, in order to understand the difference between them, let's spell this out. What we have here is y squared over q over the sum of 1. So in this case, that's also here. In this case, we have done the division for each person or for each item, and then added up the quotient and averaged it. In this case, we have done the summation first over all the items, or all the people, then the summation here again, and we've done the division after summation. This one is equivalent, so we could also write this way, it's the sum of q z squared over the sum of q. And when you write it in that form, you can see that we have weighted each of the z squares by this q, and q is not only the variance of x, but it's the information carried in that response about the model that we're using to understand the response. So this is called infit because it's an information-weighted fit statistic which focuses on the inner part of the response vector. That is, it focuses on the items near the person or the persons near the item. This is called outfit because it is outlier sensitive, since there is a single unexpected right or wrong answer on a very difficult or very easy item. This denominator will be small, making the quotient very large. There'll be one large term in this sum, which will make the whole sum large. And as a result, this is very sensitive to outliers or to unique, extreme, unexpected responses. Now, the final part of this is the measure of bias. For bias, in a block like this, say the bias of the sewing items in favor of girls, you add up the sum of the y's inside of that block, and you divide it by the sum of the q's inside of that block, and that gives you the loaded bias. And if this is positive, it means that girls are favored by those items. If it's negative, it means that girls are not favored. The standard error of this bias is equal to the same denominator there with a minus 1/2 power. So if you want to test the significance of this amount, you just divide it by this and do a t-test on it. And then the noise in the block is the sum of y squared over the sum of q, just like up here. And so you could take a block of data identified by your hypothesis about which items interact with which person to produce an unexpected situation. And you can ask, is there a bias here showing favor or prejudice with respect to these items for these people? What's the standard error of that bias? And is there noise inside of this block? Are these people showing unusual homogeneity, low noise, or heterogeneity, high noise, with respect to these particular items? As far as I can see, that exhausts the information in the original data with respect to misfit. And of course, the fruitfulness of this approach depends on your ability to identify items which have potential bias in them and persons who have potential response to bias in them. If you have no idea which items are biased or which people are being favored, then you're going to have to ransack these matrices looking for large values of y or z. In fact, if you're going to ransack the matrix looking for large values, I would look at the z matrix for large values of z, and hope that when you see which items in person combination produce the large values, that will stimulate your imagination to think of what the explanation of the bias is. But far more powerful is the approach where you say ahead of time, these items are thought to be connected with these people in some way or other, either to give them an advantage or to give them a disadvantage. And as a result, we would like to answer the question, is it so? Is there any evidence in the data that these items favor these people, or that these items are prejudiced against these people? And the complete statistical answer is to add up the Y's in this neighborhood, divide them by the Q's, and that will give you an estimate of the amount of bias in logits. That's the same scale that you've measured all the people and items on. The standard error of that estimate will be given by 1 over the square root of Q. Minus means 1 over, 1/2 means the square root. And if you have also the question of whether there is unusual similarity in their responses, low noise, or unusual heterogeneity in their responses, high noise, you can do this for the same subset, sum of y squared over sum of q, and that will give you a mean square like this. This would become v for that particular group. And you can quite often what happens is the following. If there is bias, when you do fit for these items and these people, you get misfit when you mix everybody together. When you identify the people who are causing the trouble and you remove them, the items will fit. When you identify the items that are causing trouble and remove them, the people will fit. And when you bring them together, there is a bias here, but no misfit inside. That is, the noise inside is okay. It can be explained by a fixed effect, common to these people and these items. And the estimate of that fixed effect is this bias estimate right here. So I think, dear George and dear Bo, that's all I know about fit analysis. Of course, there's a long way to go from this abstract summary to the actual content details of application. But I don't know of any other statistics available to support the analysis. From now on, that's a question of imagination, insight, and clearly defined intentions.